Hi, I'm Miss Hearn. Let's get started. In this video, which is part 2 of a set of videos on simplifying radicals, we're going to focus on higher indices like cube roots, fourth roots, and so on, and also on how to add and subtract radicals once we've simplified them. From the first video, we know that there are basically two facts that you need to simplify radicals as long as there are no fractions in them. One is that the nth root of a product, a times b, is the same as the nth root of a times the nth root of b. For example, if you take the square root of 4x, that's the same as the square root of 4 times the square root of x. Now the square root of 4 we know is 2, so that's the same as 2 times the square root of x. This would be considered the simplified form of the square root of 4x. It can't be simplified any further because there are no factors under the radical that are perfect squares. The second thing you need to remember is if you take the nth root of x to the m power, then you can find the result of applying that root and simplifying it by dividing m by n. So for example, if you have the cubed root of x to the 15th, then you can just take x to the 15 divided by 3 power, or in other words, this is the same as x to the 5th. If you combine these two facts, you can simplify just about any radical. So for example, here we have the 5th root of x to the 13th. I can't divide 13 by 5, but I do know that I can break apart radicals into separate pieces. So what I'm going to do is I'm going to think about this power of 13 is higher than 5. What multiple of 5 is the biggest multiple less than 13? Well, the multiples of 5 are 5, 10, 15, and so on. The biggest one that's less than 13 is 10. So I'm going to break apart this x to the 13th power into x to the 10th power times x to the 3rd. Remember, when you multiply like bases, you add the exponents. So this is equivalent to x to the 13th power. Now, using that first fact that we can break apart any radical that has a product inside, we're going to take the 5th root of x to the 10th, and we're going to multiply it times the 5th root of x cubed. 5th root of x cubed cannot be simplified any further, but since 10 can be divided by 5, this is the same as x squared times the 5th root of x cubed. So let's practice this with some more complicated examples. So here's one that I pulled out of Alex from our homework. And we have 18t to the 12th w cubed. This is actually a square root this time. When the index isn't written, it's assumed to be 2. We do have this number here, which I like to write my numbers that come out of the radicand as their prime factorization. So primes are numbers like 2, 3, 5, 7, and so on that are divisible only by themselves in 1. I'm going to write 18 as a product of primes. The method I like to use to do this is called the ladder method. I'm going to divide 18 by 2 and get 9. 9 is not divisible by 2, so I'm done with the 2. Going to check if 3 goes in. 3 does go into 9 3 times. And whenever you get to a prime as your result when you divide, you're going to stop, because that means you're done. So what this means is that 18 can be written as a product of these primes, 2 times 3 times 3. And you could confirm that 2 times 3 is 6 times 3 is 18. But I like to use the exponent version because we're trying to simplify radicals. So I'm going to take this radical now, square root. Instead of 18, I'm going to write 2 times 3 squared times t to the 12th times w cubed. Okay, now the next thing I need to do is really focus on which of these powers are perfect squares. In other words, have a value that's divisible by the index 2. All right, so The power of 2 is divisible by 2. The power of 12 is divisible by 2, but 3 is not. But 3 is bigger than 2. So I'm going to break apart this w cubed into w squared times w to the first. Isn't that true that that's still 3 factors of w? So I'm going to think of this as the square root of 2 times 3 squared times t to the 12th times w squared times w, or you could write w to the first, but it's not necessary. And then I'm going to use the fact that I can break apart any radical that has a product inside of it into 2 separate radicals and split up the factors. And what I'm going to do is I'm going to put any perfect squares, which means things that have powers, expressions with powers divisible by 2 over here. And then I like to call the other things the leftovers that have powers not divisible by 2. All right, so for example, the number 2 has a power of 1. It's not written, but you could think of it as a power of 1, which is not divisible by 2, so it's going to go in the leftovers. 3 squared, it has a power divisible by 2, so it's going to go in the perfect squares. T to the 12th, 12 is divisible by 2, so that's going to go in the perfect squares. W squared is obviously a perfect square. 2 is divisible by 2, so that goes there. And then W is going to go over in the leftovers because it has a power of 1, which is not divisible by 2. Now the reason why we do this is because in the next step we use the other rule. We're going to divide the index of 2 into each of these exponents. So we're going to have 3 squared square root is going to just be 3 times t to the 12th square root. Well, the square root of t to the 12th, you divide 12 by 2 and you get t to the 6th. And then w squared divided, square root of w squared, you're going to divide 2 by 2, you get w to the first, or just w. And then you still have that square root of 2w tagging along. So this is your final answer. Usually we won't write the dot for the multiplication. We'll just leave it as 3t to the 6w times the square root of 2w. Moving on to the next one, we have the 5th root of 64v to the 13th power. All right, well, you first have to rewrite this 64 as its prime factorization. So I am going to start by listing a few of the primes, 2, 3, 5, 7, etc. These are prime numbers. They're divisible only by themselves in 1, and I'm going to start dividing 64 by them, starting with 2 because it's an even number. 2 goes into 64 32 times, 2 goes into 32 16 times, 2 goes into 16 8 times, 2 goes into 8 4 times, 2 goes into 4 twice, and that's a prime, so we can stop. None of these other primes need to be used because 2 is the only prime that divides into 64. And how many 2's? 1, 2, 3, 4, 5, 6. So that means 64 is 2 to the 6th power. So I'm going to replace inside my radical, I'm going to replace the 64 with 2 to the 6th, and then we have v to the 13th. Now we want to be thinking about powers that 5 will go into evenly, in other words, multiples of 5, 5, 10, 15, and so on. Here we have 2 to the 6th. 6 cannot be divided by 5, but 6 is bigger than 5. We could think of that 2 to the 6th as 2 to the 5th times 2 to the 1st, breaking off one factor that we don't need that makes it not divisible, makes the power not divisible by 5. And then what about v to the 13th? Well, the biggest multiple of 5 that will go, that is still less than 13, is 10. So I'm going to break this apart into v to the 10th v cubed. All right, now I'm going to break apart my radical into my perfect powers of 5 and my leftovers. So for 2 to the 5th power, that power is divisible by 5 for sure, but 2 to the 1st is not, so I'm going to write a 2 over here. V to the 10th, we by design have made it so it's divisible by 5, that its exponent is divisible by 5, and V to the 3rd, not so much. All right, so now we can go ahead and take the 5th root of these perfect 5th powers. The 5th root of 2 to the 5th is just 2, and the 5th root of v to the 10th, 10 divided by 5 is 2, so that's going to be v squared. And we still have the 5th root of 2v cubed left over tagging along here. And again, this is all multiplication, but we don't usually write that multiplication, so I'm going to erase that dot there. We have 2v squared times the 5th root of 2v cubed. Okay, let's look at one more. So we have the cubed root of 40t to the 6th. First thing we need to look at is getting this 40 written as its prime factorization. Remember, primes are numbers like 2, 3, 5, 7, and so on that are divisible only by themselves in 1. The smallest prime is 2. Whenever we have an even number, I like to start by dividing by that 2 and see how many times it goes in. 2 goes into 40 20 times, 2 goes into 20 10 times, 2 goes into 10 5 times. And if you get to a prime number, you're going to stop because you have your answer. 40 is 3 copies of 2 times 1 copy of 5. So we're going to write this as the cubed root of 2 cubed times 5 times t to the 6th times w to the 11th. All right, now we focus on the index. We have an index of 3 here. So we're interested in having powers of 3 or multiples of 3 in the exponents inside the radical, because those are the ones we can simplify. So 3 is divisible by 3. 1 is not, but it's smaller than 3, so there's nothing we can do with that. 6 is divisible by 3. But 11 is not, but 11 is much bigger than 3. So you think about the multiples of 3. 3, 6, 9, 12. The biggest one less than 11 is 9. So I'm going to break apart that w to the 11th. I'm going to think of it as w to the 9th times what? Well, what adds to 9 to give you 11? 2. So think of it as w to the 9th times w squared. Now we're going to break apart this radical into the perfect cubes and the leftovers. So the perfect cubes I'm referring to are those factors with powers divisible by 3. So 2 cubed, the first factor here, is going to be a perfect cube. 5 to the 1st, however, doesn't have a power divisible by 3, so it's going to go over there. And you don't actually have to write the first power. T to the 6th, is that a perfect cube? Yes, because 6 is divisible by 3. W to the 9th has a power that's divisible by 3. But w squared does not, so that goes into the leftovers. So now we're going to simplify the radicals by taking the cubed root of the perfect cubes. Cubed root of 2 cubed is just 2. Cubed root of t to the 6th, well, 6 divided by 3 is 2, so it's going to be 2t squared. W to the 9th, cubed root of that, well, 9 divided by 3 is 3, so this is going to be w cubed. And then we have cubed root of 5w squared left over. So that would be the answer. Next, we're going to talk about adding and subtracting radicals, which is something you can't do unless you know how to simplify radicals. So now that we have that skill down, let's talk about addition and subtraction of radicals. This is actually something you already know how to do, I promise. You just don't realize it, because you know how to deal with something like 9x minus 8x, right? How do you subtract 9x minus 8x? Well, you just subtract the coefficients. 9 minus 8 is 1, and then you just keep the x the same, right? The reason why that works, by the way, is because of the distributive property. You can factor out that x and you see you just get 1x. But what's important to us today is not why it's true, but that when you do that, this is saying it's true for any number x. As long as it's the same number, it will work. So for example, down here we have 9 square roots of 7 minus 8 square roots of 7. Okay, what if we let x be the square root of 7? Then we would see that 9 square roots of 7 minus 8 square roots of 7 gives us 1 square root of 7. These are what are called like radicals. And you can only add or subtract when you have like radicals. You must have like radicals. They have to have exactly the same index, which these do. And they have to have exactly the same radicand, which these do. The 7s are the radicands, to be like radicals. And then all you have to do is add or subtract their coefficients as indicated. So in this case, we get 9 minus 8 times the square root of 7, or 1 square root of 7. And you don't have to write out all those steps. This is just my justification here, but you can just say, oh, 9 minus 8 is 1. That's just the square root of 7. So let's look at another example. Here's an example where we don't have like radicals. They all have the same index. They're all square roots, but the radicands are all different. Well, guess what? This doesn't necessarily mean you're stuck, because it's possible these have not been simplified yet. So let's go ahead and try to simplify them. So how do we simplify the square root of 45? Well, I'm going to use the technique of writing the prime factorization of 45. So I'm going to jot down the first few primes here. Okay, does 2 go into 45? No. How about 3? Does 3 go into 45? Yes, it goes in 15 times. Does 3 go into 15? Yes, it goes in 5 times. Oop, I can stop. I reached a prime number. So what that means is that 3 times 3 times 5 is 45. Or in other words, 45 is equal to 3 squared times 5. So to simplify the square root of 45, well, actually what we're working with here is 5 times the square root of 45. What we're going to have to do is to think of it as 5 times the square root of 3 squared times 5, and break this apart into the perfect squares and the leftovers. 5 square root of 3 squared, square root of 5. Square root of 3 squared is just 3, so we have 5 times 3 times the square root of 5, or 15 root 5. So instead of writing 5 square root of 45, we're going to write it in its simplified form, 15 root 5. Plus, now this one, you can't simplify square root of 5 any further. That's a prime number, so that's just going to be 4 root 5. But we do still need to work on square root of 20. Square root of 20. To simplify it, I'm going to write it in its prime factorization. 2 does go into 20, so it goes in 10 times. 2 goes into 10 5 times, and we can stop because we got a prime. So that means that 20 can be thought of as 2 times 2 times 5, or 2 squared times 5. So here we have the negative square root of 20. We're going to think of it as negative square root of 2 squared times 5. Break this apart into the perfect squares and the leftovers. Square root of 2 squared is just 2, so that's going to be negative 2 root 5. So I'm going to write that over here, negative 2 root 5. All right, so now we have all like radicals. So we can just add and subtract the coefficients, right? 15 plus 4 minus 2, you don't have to write that step, but times the square root of 5. That's going to be 19 minus 2, or 17 square roots of 5. Why don't you try this one? Go ahead and work it out. You can pause the video and then I'll show you the solution and you can see if you get the right answer. Okay, the first step is to find the prime factorizations of 512 and 162, which I've worked out here, and it turns out that 512 is 2 to the 9th power, and then 162 is 3 to the 4th power times 2. So I've replaced 512 with 2 to the 9th and 162 with 3 to the 4th times 2, and now I'm going to work out simplifying the radicals. Since we have an index of 4, we're interested in powers that are multiples of 4, like 4, 8, 12, etc. So when I look at 2 to the 9th, the biggest power that would work for me that's less than 9 is 8. So I'm going to think of this as 2 to the 8th times 2 to the 1st, or just 2. Minus 2 times, over here, I have a 3 to the 4th and I have a 2 to the 1st. Neither of these is a power bigger than 4, so I don't have to break anything apart as far as the bases go, but I do break this into 2 separate radicals. The one with the perfect 4th power times the one with the factor that's not got a power of 4. The perfect and the leftovers. All right, I'm going to do the same thing over here. This is going to be negative 4th root of 2 to the 8th times the 4th root of 2. 4th root of 3 to the 4th is just 3, and there's nothing I can do with the 4th root of 2. Over here we have negative 4th root of 2 to the 8th. Dividing the 8 by 4, we get a power of 2. So it's going to be negative 2 squared times the 4th root of 2. And then 2 times 3 is 6 4th roots of 2. And so this is going to be negative 4 4th roots of 2 minus 6 4th roots of 2. Now we have like radicals. They have exactly the same index 4 and the same radicand 2. So I can just subtract their coefficients. Negative 4 minus 6 is going to be negative 10 4th roots of 2. And we're done. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That helps other students to find the video.